My name is Mauricio Alvarez. This is joint work with David Luengo. I should mention that he was a postdoc at Manchester when I was doing my PhD back in 2009, I think, at Yale. I should mention that a lot of the material I'm going to use has been already used by basically, you have these two ways of seeing data modeling. So you have this data-driven paradigm, which is used a lot in machine learning when you have some data set and you use a flexible class of models, and using regularization, you make predictions over unseen data. So that's like the traditional way to do data modeling in machine learning. So there are two problems, basically. The first one is that if the data is scarce relative to the complexity of the system, predictions are going to be very poor. And on the other hand, if you try to use your model for doing extrapolation, predictions are quite inaccurate. So that's one end of one way of seeing. The other way is using mechanistic models. So basically, these are models which are inspired by the underlying knowledge of a physical system. And they try to characterize a physical process using basically a set of differential equations. So the problem here is that usually it's quite difficult to try to describe all the interactions that are going on in the system just using differential equations. But a good thing of the mechanistic models is they allow you to do extrapolation, something that you cannot do so easily using the data-driven models. So what are latent force models? So they're basically like hybrid systems in which sort of combine the knowledge given by the differential equations and Gaussian processes. So what you are trying to do is to construct very structured covariance functions that somehow encode some prior knowledge that you have about the dynamics that is happening in the problem. So we have worked out some examples with dynamical systems, first order, second order differential equations, and some others with partial differential equations, particularly with the diffusion equation. So, okay. So that's the basic idea, yeah? So you want to construct very structured covariant functions using the prior knowledge given by a differential equation. That's the latent force model, yeah? And use that covariance function. Sorry? I use that covariance function for working on with GP regression. That's the whole idea. So this motivation, how do you go from latent variables to latent forces? I think Neil talk about this. So you start with a basic latent variable model. So you have your data Y, and you have, well, I'm using a different notation to confuse you a bit. So you have your data here, you have your latent variables U, you have your matrix W, and you have some noise. So this is the basic latent variable model. And then, as Neil was saying, in PCA you sort of put a prior over U and you marginalize, and then you optimize W. And then, for example, if using the GPLBN, you do the other way around, as we saw yesterday. So in those models, usually you assume that the rows of your data matrix are independent, but you can introduce some dependence using a GP prior. So if you assume that those data points depend on time, then you can use a Gaussian process which is independent over the columns of the matrix U, this sort of prior, and then you can work out the covariance for Y, yeah, for the outputs. In the second part of this talk, I'm going to talk about models that have been used before in geostatistics that has a very similar form to this, and then you can do a lot of different extensions. And then you can include, the important thing here is that you can include, if you have a mechanistic inspiration of what is going on in your system, you can include some matrix of spring constants, And then there is a relationship between this model and the latent variable model that we had before. So this is like an example. So you have D outputs. Remember that this Y matrix was n times D, where D is the dimensionality of the output space. So for each output you have a spring constant associated, and then you force that system using a set of forces like this. So that's sort of what is going on there. So that's the model with the spring constants. But you can keep adding more. You can add some differential information. That's what we do here. We add the dampers and the masses, and we get this second order system. And the idea here is that you can encode, as Neil was saying, you can encode some other effects like inertia and resonance that you don't have in the usual latent variable model. Yeah, because that's like a very instantaneous way of transmitting information from the input forces to the outputs. And that's what we call latent force model. Okay. So what I'm going to do now is to do like the operational latent force model. So I'm going to give all the equations that you need to actually use this in practice, because this is sort of like the big picture. So we have this general dynamic latent force model. So we have this, we call this...
I'm sort of unclear. What is it we're trying to learn here? Is it U? Is that always what you're trying to learn? Or is it the other parameters of your... I've got a little bit lost in what the quantity of interest is in all the notation.
Yeah, so you are trying to model different outputs. Yeah, so you have several outputs, you are trying to model them. Sure. So you can, sometimes you are interested in doing inference over the latent functions. So for example, in systems biology, you want to do that. Yeah, but what you really want to do is to use these models to do extrapolation. That's what you want to do. Yeah. The other way to see it is what you're saying. You can also use the GP framework to do parameter estimation in differential equations. Yeah, because as we will see, when you optimize the marginal likelihood, so you sort of have a point estimate of your parameters in your differential equation. Yeah, so maybe those parameters reflect something about the system, maybe not, but yeah.
Right. It depends a bit on the example. In systems biology examples, you're often interested in the sensitivity matrix because it tells you which transcription factor is regulating which gene, because you observe the gene expression, but you don't observe the transcription factor. But you might also be interested in what the transcription factor is doing. So you might be interested in the latent function as well. And in some cases, we do Bayesian inference over the kernel.
Yeah, okay. So this is the general form of the dynamical latent force model. So we had before two examples. This is, I've used this notation. So this is a matrix Y, but the elements of that matrix are the derivatives of the output. And these matrices AM are diagonal matrices. So in the example that I had before, we have this M matrix, which refers to masses of the outputs, and the C matrix referring to the dampers, and the B matrix referring to the spring constants. Yeah. So this is like the notation we had before. So I'm trying to do like a connection between the notation that we had before in matrices with what we actually do when we derive the covariance functions. So the elements in this equation have this form, yeah, in general. So I'm going to use, oh, sorry about this S, shouldn't be here. So this DMO0 operator, it's a way to summarize this sum here. So you have some constants and you have these differential operators acting over your output, and that's equal to the sum of the latent forces that you have plus some noise. Yeah. So the important thing here is that you can always, at least for linear operators, differential operators, you can always assign a Green's function to your differential operator. So this is the differential operator we had before. This is the so-called Green's function, and there is a way to obtain this Green's function using this equation that we have here. So in control engineering, probably this is called the impulse response to the system. So the Green's function is usually associated to how a system reacts when it's excited using an impulse response, an impulse function. And then we can write the solution for the outputs in this way, where this fd is given by this integral that involves the Green's function, which is associated to your differential operator. So the uncertainty here is given by this Gaussian process that we place over UQ. And that's why you get this uncertainty in the outputs. So we use this additional stochastic process if we want to add some independent effect that we cannot capture using the using this basic and set of related latent functions. Is that clear? Anybody has a question?
Did that white noise, I assume, has come directly from your error before?
Yeah, you could see it like that. Yeah. But the thing is that if you do it like that, maybe the type of noise that you are modeling has a very particular structure. Yeah, because it will depend on the differential operator. But in this way, it's just whatever general process you want to include. You know what I mean?
It's a bit like what Rich was doing, including a general process to say, this is the difference between my physical system and what I observe. I'm going to put in a Gaussian process. And that's why I said, we call that, or we think of that as a crud capture. So, but Mauricio is using the better term, general stochastic process. So things that aren't fitting your underlying latent force model, which is trying to correlate everything, you can think of it as like a process noise. Because the underlying latent force is trying to correlate all these outputs together and say how everything's moving together. But maybe they're not. Maybe they're actually all just doing independent things. You don't know your physical model's right. So then you have potentially independent processes predicting each output, and then on top of that, white noise again to look at independent variation.
Yeah.
But would you not have accounted for that in your original model definition before you solved it?
No, because it's sort of the same hierarchical idea, but it's the same level. So you have one thing which is common to all the processes, yeah, but then there are some effects that maybe you can't explain using that. So you need to allow for some flexibility. You know what I mean? Okay. So here is, so remember that here we put the Gaussian process prior. But since this is linear, you can work out the covariance for y. So this is the basic idea is that you assume that your latent functions are independent and each of them follow this Gaussian process prior. We also assume that this process is YD, I showed before, are independent. And then we can work out the covariance for Y, which is going to be the covariance of FD, one output FD and other output FD prime, plus the covariance of this process YD. And this is the form of the covariance, yeah? So here you have the Gaussian process covariance of your latent functions, and you have the Green's functions associated to your differential equations. So the thing here is that you have to be able to solve this double integral, yeah, because what we want to do is to construct actually this covariance function to use it in practice and do all inference and parameter estimation and all that, yeah. So this is deterministic because it's associated to the assumed differential operator that you're working with, and the uncertainty is given by the Gaussian process, the covariance of the Gaussian process. Is that okay? Yeah. Okay. So this is the dynamical latent force model. So the input is just time, but we could do multidimensional inputs. So we have the inputs that belong to RP, yeah, and for that we can use linear partial differential equations. So for the linear partial differential equation, you can also assign or associate a Green's function. and then you could solve the covariance function in the same way. Yeah.
I have a question about the double integral.
Yeah.
Can you solve it analytically? I'm sure you can probably with few functions, but can you do that?
Yeah, it all depends on, yeah, I mean, the maths are very heavy, but you can do it. So we have done it for first order, second order.
Okay.
Yeah.
So that surely depends on the covariance function and the Green's function, right?
Yeah, that's true, yeah.
So for which kind of situations can you do it analytically? And in general, does the Green's function, or the integral in general, does it have any mathematical properties I can leverage in order to compute it numerically?
I don't know if there is like a general case. I mean, certainly there are some properties that your Green's function has to fulfill in order to do this. Yeah. The properties are that it has to be absolute integrable. Yeah, because it has to be, you know, it has to decay when it goes to infinity.
Well, the product of the two has to be.
Yeah, well, I'm talking about the properties only of the Green's function.
Okay.
But when you solve the integral, yeah, the product of the both. Yeah. I don't know if there is like a general theorem maybe that you can use to know that. I don't know.
But do these Green functions in general have any properties that are good in some sense? Are they always continuous? Are they always doing something?
Well, we assume they are continuous.
Well, nice thing in the state-space representation is that actually the Green's function is the lower left corner of the matrix exponential function. So it's very easy way to actually calculate that. But you need to convert that into state-space form first.
Yeah.
And that's actually what was my starting point why I chose the top one. So it's, well, okay. So the Green's function can't be expressed in terms of the matrix exponential function.
Okay. Okay, so I was saying you can use partial differential equations and you can associate a Green's function to your partial differential operator, and basically you can work out the covariance in the same way that I showed before. So now we just change the input time just for a high dimensional vector x. So now you have multi-dimensional inputs and you also have multi-dimensional outputs. That's basically your GP. So how do we do learning in these latent force models? So you say you have a set of inputs x, and you have some theta that represents the hyperparameters of your covariance function. So in this setup, the hyperparameters would be the parameters associated to your differential equations. And remember, you have a differential equation for each output. And the length scales that you assume, the parameters that you assume for your covariance function of the latent functions. Those would be your hyperparameters. Okay, so and then you can, to do the learning of the hyperparameters to work out the marginal likelihood of the Gaussian process of the outputs, the matrix Y we now transform into a vector Y, yeah, and then this covariance matrix has dimensions ND times ND. Remember, D is the number of outputs, and now I'm assuming that all the outputs have the same number of data points. Maybe that's not so relevant here. So this is your covariance matrix, and then you have a matrix associated to these processes YD. Yeah. So this is a way to do. I mean, this is a form of multi-output Gaussian process. Neil was talking about that on Tuesday. So you have several outputs, and you have this big matrix, this covariance matrix, which accounts for the correlations between outputs and inputs. Yeah. So you do the usual thing that you saw with Gaussian processes. You optimize the log marginal likelihood with respect to the hyperparameters. That's a way of doing hyperparameter learning. Is that okay? You can also use your latent force model to do predictions. So once you realize that a Gaussian process is quite easy to use all the machinery we have seen in the last few days to do sort of the same task that you had in normal Gaussian processing. So you can compute the predictive distribution. So again, you have your mean predictive and your covariance function. So if you want to use a latent force model to evaluate some new test data, yeah? Okay, so I was saying that you have this big matrix KFF, dimensions ND times ND, so you have problems with the computational complexity. So you can use, again, sort of all the tools that you have for sparse or for efficient computation better here as well. So this matrix, the inversion of this matrix scales this way. We saw the single output case with James on Tuesday. And we have derived several methods to do efficient approximations here. So one of them is what we call PITC for multiple outputs, partially independent training conditional. So instead of assuming that you have to know all the latent function, basically what you have to really know is how the latent function is how it behaves with respect to some set of particular points in your latent function. It's something like what is drawn in this diagram. So this could be the way in which you solve normally the latent force function, latent force model. So if we see this as a generative model, you would sample from your Gaussian process, which is the latent function, and then you pass those functions through your Green's function, you solve the integral, and then you find your function for your output. So if you do that several times, you translate the uncertainty that you have in your latent function to the outputs. Yeah, but that's the problem. If you try to marginalize this, then you end up with that huge covariance. So the thing is that in these approximations, what you say is, okay, what happens if I only knew some points of the latent function, and based on those points, I try to make regression over the whole latent function. So instead of working with this infinite dimensional element, which is your latent function, you work with this mean expected value of your latent function given some discrete points. So that's basically you work with this conditional probability function. And then as long as your latent function is smooth, it's going to be a correlation between any point in your infinite dimensional function with the set of points that you choose to make the representation. So that's one way of doing it. And then if you work out the maths of this, you get to an approximation which is low rank for the covariance function, covariance matrix. That's one way of doing it. Another way of doing it is try to use this lower bound, which you see has a low rank approximation for the covariance matrix, and then this trace term, which penalizes the approximation. This is derived assuming a lower, trying to find the posterior over the vector u. Yeah. So there is also a paper about that. Okay. Any question? So that's like the general background. Yeah, so you basically have to work out the covariance function. And then once you have that, using your differential operators or your Green's function, you can basically use all the Gaussian processes machinery that we already know to solve interesting problems. Yeah? So the key thing there is to be able to get that covariance function. That's the important thing. So we're going to see some applications. So these applications in second order dynamical systems. So Neil was talking about this before. So you have this second order model that you want to use to model motion capture data. So if we use the framework I explained before, we will do this. So we express the output as this linear combination of the latent functions fd, and each latent function is obtained when you solve this integral. Yeah. So here you have your Green's function. This would be your Green's function associated to your differential operator, second order, and this is your latent function. Yeah. So each differential operator will have a different Green's function associated. Where this omega d is given by, remember that VD are the spring constants and CD are the damper constants. So I'm assuming here that the masses are 1. Yeah, all the masses are 1. And then you have different, you could have different responses of the system depending on this coefficient called the damping ratio, which is defined in that way. So if the damping ratio is 0, it means that basically once you excite your system with the input function, the output is going to oscillate and it's not going to stop ever. Yeah, it's keep oscillating all the time. If the damping ratio is less than 1, so you have oscillations and eventually those oscillations reduce the amplitude and it gets to a stable state. Yeah, as if you excite the system with a step function, let's say. If its damping ratio is 1, it's critically damped, so it doesn't oscillate and it quickly reaches the stable point. And if it's greater than 1, it's an overdamped system. So if you excite the system with a step function, it will get to the stable output, but stable state, but it will be very slow to get that to that state. Yeah, so that's the difference between these things. And here we have the covariance that Neil showed before. This one is the covariance of the latent function, which here we have assumed follows RBF covariance. And then this is the covariance of the first output, which is under damp. So you see the oscillations here. In the covariance function, you have an overdamp, yeah, which takes some time to get to the stable state. And you have critically damped, yeah, which sort of looks a bit like this, yeah. A bit, not too much. And we have samples from this covariance function. So in cyan I have the latent force. In red we have the underdamp. In green we have the overdamp. And in blue we have the critically damp. So these two, they don't follow too much. I mean the last two, the green one and the blue one, which are the critically damped and the overdamp, they don't follow too close what is going on in the latent function. It takes some time to react. But the other one, which is the underdamp one, the red one, it really follows what is going on in the input. Yeah, these are some other samples, and I was doing a nice explanation of these resonance effects that you see here. Okay, here, yeah. Okay, so I'm going to skip through this because Neil already explained this. So I'm going to talk about partial differential equations. So that was an example, Neil was giving an example with dynamical systems, a second order dynamical system. Now I'm going to talk about partial differential equations and a bit about stochastic differential equations for some examples we did in the past. So this is a very classic problem in geostatistics. So this is a region of the Swiss Jura, and a long time ago there was a lot of mining activity there, and some pollutant metals spread all over the place. So what we want to do now is to explain some measurements, some concentration of these pollutant metals. And for that we are going to assume that the data what we see now is the result of diffusion processes. So at some point the metals were concentrated in these locations and they started to diffuse over the region. That's, let's say, what we think about what is going on. And the data we have now is like a snapshot of that process. Yeah. So in geostatistics, this is usually called co-kriging. So the problem they have is that usually you have a lot of what they call secondary variables and primary variables. So usually you have a lot of data of the secondary variables. Think, for example, on the pH level of the soil. And you also have some primary variables, which are, for example, the concentrations of these metals. Yeah. So it's very easy to measure pH, for example, but maybe it's more difficult to measure the concentration of the metals. So what you want to do in co-kriging is to use that secondary data as a proxy to try to make predictions for these primary variables in which you are interested. So because they are correlated, you can actually use that. Is the problem clear, or does anybody has okay? So this is like a cartoon of what is going on. Yeah. So we will assume that the outputs follow a diffusion equation. Actually, this is a simplified version of the diffusion equation. So this is our output, and here we have the partial derivatives second order on the spatial dimensions. The solution is given by this. So this is basically the same that we had before, but now the Green's function is it's a Green's function derived from a linear partial differential equation that has this form. It's exponential, and the argument is quadratic in the input variables. So here we are treating, actually, maybe this is a bit misleading because the time is not, we are not taking into account the time. The time we assume is fixed, because this t here will appear as a hyperparameter actually of this covariance function. So we are only caring about the spatial variables. That's really what is going on there. So we use this, we derive the covariance function using the same procedure that we did before for the dynamical system. We use our Gaussian process, we estimate the hyperparameters, and then we do prediction in the usual way. So this is an example. Some results we have here. So this is the task I have. I want to predict this primary variable, which is cadmium based on nickel and zinc, for example, and so on. Yeah, so these are the primary variables and the secondary ones. And here I'm comparing, I think this is absolute mean error. I'm comparing the absolute mean error between some test data and the predictions made by 3 different methods. Here we have independent Gaussian process, where you assume that each of these ones is independent of each other. You have the Gaussian process with diffusion kernel, that sort of diffusion kernel we derived before, and we have this method using geostatistic called ordinary co-kriging. And so these are the results. Yeah. So in 3 of them we make slightly better predictions. Is there any question?
What's ordinary co-kriging in terms of the linear model and the other? I can't remember.
I think it doesn't have to do with the linear model. I mean, with the form of the covariance function.
Yeah, so it's not. It's co-regionalization.
Yeah. They use linear model co-regionalization. Yeah. Right. Okay. So one last example is with stochastic latent force models. So this is an example with financial data. We have we have the prices of some currencies, 10 top currencies, and 3 precious metals. So that's some of the data we have. And we derive this differential equation, but now we have assumed before that the latent force was following a Gaussian process with RBF covariance function. But here we will assume that this is noise, white noise. So this is what I think Simo was talking about yesterday. So you have UT as a white noise process. Then this turns out to be the Lagrange equation, which is a linear stochastic differential equation. Yeah, and then you can work out the covariance for this FD, which is the OU covariance. And these are the predictions that you make. So I'm only showing 4 of the outputs. We have 13 outputs, but I'm only showing 4. So in some of the outputs, we have some missing data. Yeah. In some of the others, we did the missing data on purpose. So what we see here in short lines is the real data. We remove that just to see if the model will be able to do the prediction. And these are the results we get. So we see that we don't know what is going on here, yeah, because we don't have the actual data for that. But we know that here, for this one, the predictions are okay. These crosses here are related to the approximations I was talking about before.
I can't remember for that. Did we try also a latent force that was smooth as well as the OU, and then it switched off the smooth latent force?
I think we didn't do a lot of experiments with that. Yeah. Okay, I think I will stop here because so there are some extensions we have done in the past, but I think I have another spot in the afternoon, so I'm going to keep this for the. Yeah. I don't know if there is any question. Yeah.
For example, the financial data, can you also do extrapolation, or did you try that? To predict?
I think David was trying that. I don't know if he managed to. But yeah.
But by the fact that we included the interpolation result, not the extrapolation result, I think you can guess that that didn't work as well. But I can't remember. It's a while ago, isn't it?
But it's maybe better than just a GP.
Well, this GP here, the point was to try and correlate those multiple outputs. So if you did just a GP, at that time we didn't have an implementation of the linear model of co-regionalization, right? So the idea with this was to really test the correlating across these 10 financial time series. So the thought was, how many latent functions do we need? So the currencies are going up and down, but they group in Europe, they group together, and it was around the time that, so that Australian dollar prediction, it goes back. Wasn't that something like, did we know about New Zealand or something? And New Zealand pulls. Yeah. The reason you know the Australian dollar goes down is because New Zealand goes down at the same time. There was some sort of Asian crisis or something that caused that to happen. But we didn't try the linear model. I'm trying to remember. We didn't.
No, no. We did some of the thing that Richard did with this PCA thing. I think that's what we did. Yeah. Yeah.
Do the green functions have special properties? Like are they symmetric?
They have some properties. I can't remember all of them now, but they do have some properties.
They
Yeah.
don't have to be symmetric because the exponential times sign isn't symmetric.
I think that's positive function.
Yeah. Maybe no. I think the most important thing is that they decay. That's the most important thing. I mean, when you do the integral, they decay.
If you think about when you look at the integral, they could be any function, and you'll still get a valid covariance function.
Okay.
So you can convolve your process because do you have the integral? Because it's just a double integral.
Because I think there was a paper on using Green's functions for kernels, directly as kernels.
Well, then they would have to be positive definite. Well, unless you do this integral here, right? You're allowed to put any function there and any function there, maybe some continuity things or whatever, and you'll get a positive definite covariance for that.
Yeah.
So there's no constraint. I mean, this in itself is a valid covariance, regardless, because this is one of the ways of constructing covariance.
I was just saying that I think Green's function is still a positive definite, but I may be mistaken.
I don't think they are, because there's, well, Timo.
I confirm that Green's function is just a fancy name for that's the matrix exponential which you learn in the first course of ODEs.
Okay.
So that's you have an arbitrary matrix you compute it's exponential, and it's not symmetric. It's not positive definite. It's not anything. It can be like cosines.
All right. Yeah, that's right.
One way you can construct kernels with Green's functions.
Cosine is not it's not positive anything. Cosine function.
Yeah, but it is positive definite.
In what sense?
That the covariance matrix is actually into the sign seen as a stationary function.
You can see it, Timo, because it's a delta function in the, or maybe it's just have to be just a little bit wider. The limit of a cosine is a delta function in Fourier space, right? So
Two delta
it
functions.
fulfills Butler's.
Okay, maybe you're referring to different kind of positive definite. I was thinking about the Green's function as a kernel such.
Well, going back, I think the Green's function as a kernel thing is because the way you probably construct that, I think, is putting a delta function in here.
Yeah, if you
And if you replace that with a delta function, then the result of this is always positive definite, right? And that's how you can construct kernels with Green's function. That's equivalent to a white noise process driving the differential equation, and then you get the covariance function.
Yeah, so that will be positive for any function, any G, yes.
Yeah.
Because it's like a double convolution. You
Yeah,
can write
precisely.
that down as a like a.
Well, and it's the continuous variant of this basis, right? It's just using that. So it's the same thing as building a covariance function in this way. It's just a continuous equivalent of that.
Yes, it's the same.
If you put the delta function there.
Or like matrix times covariance matrix times matrix transpose. That's completely the same thing. And it's always positive.
But just like you can put any basis in here and get a positive definite matrix, you can put any function into the Green's function. But maybe, I don't know if differential equations, stable differential equations probably illustrate that.
So I thought it was about like a Green's function as a kernel. It's not positive definite. It's something arbitrary.
But you know, it's also a kernel, it's a smoothing kernel. That's the confusion, right? There's a different type of kernel that people can use. People call that a kernel. And when they say it's a kernel, they mean like a smoothing kernel.
Yep.
Because you do.
has kernel typically when you have a dynamic system.
Yeah, but that's a different meaning of the word kernel, which is like,
Well,
it has the same meaning.
it's the kernel of the linear operator anyway.
Yeah.
Both covariance functions have associated with linear operators, so it's actually easily equal to the same thing.
Okay. Yeah, Shiro.
I was wondering, do the properties of the system pop out of your hyperparameter optimization, or like for instance you showed underdamped systems?
Yeah. Yeah, that's true, yeah.
And I was wondering if, for instance, if you have prior beliefs over the type of system, if you could pose that.
Sorry?
If you had prior beliefs over, if there are cases where, I'm not sure that they were right, but I'm imagining if you believe your system is underdamped or something, and it pops out of to impose that in the optimization.
You could do that, yeah. You could just fix those parameters to the values you think they are. Yeah.
Because popping out as a ratio of two parameters
Yeah.
that were in.
Yeah, because actually you make the optimization of the springs and the masses and the dampers directly, not over the damping ratio or the frequency. Yeah. Is there any other more questions?
I'm also in the schedule. Is it coffee now?
Okay.
Coffee?
Yes.
Okay. Coffee break and then 5 to 11.